Hi, I'm Quantic Dev, and this is the sliding window technique of my algorithm questions series. Sliding window is one of the essential dynamic programming techniques. It is also one of the common algorithm questions in programming interviews. Any software engineer will have to deal with some form of sliding window of data at some point in their careers, sliding with the job interview, of course. It is essential to have an in-depth understanding of algorithms since competitive companies tend to ask more varied and harder questions. If you have a great deal of knowledge of different classes of algorithms, you can apply them to many variations of common interview questions easily. Today, I will give you an in-depth guide of the sliding window technique. I will describe how it works and what classes of problems can be solved using it, along with sample questions and their solutions and their tests. Overview. Sliding window technique is a method for finding subarrays in an array that satisfy given conditions. We do this via maintaining a subset of items as our window and resize and move that window within the larger list until we find a solution. Sliding window technique is a subset of dynamic programming. Dynamic programming is a method for simplifying complicated problems by breaking them down to simpler subproblems. If you can find a subproblem with a solution that can be applied to the bigger problem, you can solve the bigger problem by solving the subproblem. In our case, maintaining a subarray window that satisfies given problem constraints is our subproblem. Moving that window over the entire data will solve our bigger problem. Sliding window technique frequently appears in algorithm interviews, since dynamic programming questions are the favorites of interviews, including me. Sliding window technique solutions have a time complexity of O(n), which is linear time, and space complexity of O(1), which is constant space. Sliding window technique is mostly used for finding subarrays inside larger arrays. You can apply sliding window to a majority of minimum, maximum, common subarray, substring type of questions. Note that some subarray related questions have very specific and optimized solutions, like that of Cadane's algorithm. We will investigate this situation while solving our problems. How does it work? Let's see how the sliding window technique works on a sample question. Given an array of integers, we will try to find the subarrays that add up to 9. We will start by creating a sliding window from the first two array elements, 1 and 2. This only adds up to 3, so let's expand the window by 1 from the right. 1, 2, 3. This new window still only adds up to 6, so we will expand the window once again. 1, 2, 3, 4. This new window now adds up to 10, which is bigger than our target of 9. So we will continue by shrinking the window one element from the left. 2, 3, 4. This window now adds up to 9, which is our target. We can now continue to expand the window when it is less than or equal to 9, and shrink it when it is above 9, and continue to find the rest of the subarrays that add up to 9. And this is basically how the sliding window technique works. Let's move on to some real-world interview questions to examine harder problems. This is an easy one, and we're going to use statically sized sliding window. Given an array of integers, find the maximum sum subarray of required size. Here's our example input. Bunch of integers, negative, positive, whatever. And the subarray size is 2, meaning that we're going to find a subarray with the maximum sum of size 2. I would like to note that you won't always be given an example input. This is the courtesy of the interviewer, and they might not provide you with an example to work with. If that is the case, it's a good idea to create your own example so you can visualize the problem on it. And as always, we're going to start with our requirements. And another tip here, always ask for clarifications in the requirements step. Sometimes the questions are going to be quite concise and they won't list all possible corner cases, and you are expected to ask for clarifications and find out those corner cases. So let's start. Always analyze the requirements even on simple questions. They might not be so simple. Especially short questions, which seem really simple, could end up being especially hard. So it's always a good idea to treat every question equally and assume that they could be hard. Also, subarrays are contiguous by definition, so elements should be adjacent. So this is valid subarray, but this is not a valid subarray. They are not adjacent, so the subarray is not contiguous. This would be a valid subset though. The input size could be anything. So our input size is unbound. It could be a bunch of integers. It could be terabytes of data. Also, another tip, it's always a good idea to list your requirements on the whiteboard. It will demonstrate that you care about the requirements, and it's also good to have them on the side so you can go back to it. Now let's do the analysis. The input size is unlimited, so the memory can blow up if we are not careful of what we keep in the memory. So if it is terabytes of data, and if we try to process it, store the processed data in the memory, we can end up needing terabytes of data. So it wouldn't be a valid approach. As a result of that, we cannot pre-calculate and store all possible variations beforehand. This is the brute force approach. This wouldn't be a valid answer in an interview situation. Do not use recursion because most programming languages and runtimes have limited call stack. For instance, Node.js has 50,000 to 100,000 call stack. And if the input size is above that, your call stack is going to overflow and your program is going to crash. And it's always a good idea to think through all the data structures that can be utilized in the solution. Now, this is a simple question, so we're going to just use simple arrays. But in harder questions, it's always a good idea to visualize in your mind what sort of data structure you can use in the solution. That will help you think better. Now let's analyze the brute force approach. We're going to start by calculating all possible subarrays with two members and store them in a hash table. Another tip here, a hash table or a hash map or a map are all the same things. Different programming languages prefer different terminologies, but they are always the same. Then we're going to iterate over the hash table until we find the subarray with the maximum sum. So let's go ahead and do it. We're going to calculate the first subarray with sum 1. Then we're going to calculate the second subarray with sum 5. And we're going to calculate the third subarray with sum 4. And we're going to do it until we process all of the array and store these in a hash table and just look up the maximum one, which happens to be 5 in this case. Obviously, time complexity of this solution is going to be O(n) for the hash table creation and O(1) for every lookup afterward. The space complexity is going to be O(n), which is disastrous because the input size is unbound and the memory use is going to be unbound. So this is not a good answer. So here is the sliding window solution. We're going to use a statically sized sliding window. So we're going to start by calculating window sum, starting with the first two elements. Then we're going to slide the window by one element at a time. So let's do it. This is the first sum, which is 1. This is the second sum, which is 5. We slide the window again. The third sum is 4. We slide the window again. The fourth sum is -2. And we do this until we process the entire input. And while doing this, we will only have to keep track of the maximum subarray that we found up to that moment. So we'll just record this, 2 plus 3 being 5. And if we don't find anything more, we're just going to return 5, and that's going to be our solution. And the time complexity is O(n), just like the brute force approach, but the space complexity is O(1), because when we are sliding our window, all we have to keep in memory is the starting index of our window and the ending index of it. In addition, we have to keep track of the largest subarray sum that we found up to that moment, and its starting index and its ending index, and that is it. 4 variables, or even 3, and that's all we have to keep in the memory to solve this problem. We can utilize the same method to find the minimum sum subarray. So if you are asked to find the maximum or minimum sum subarray, you can think of utilizing sliding window technique in general. So here are some tips. The objective here is to teach how to think towards a solution in all similar cases of problems. Obviously, in real-world interviews, you're going to give variations of these questions, and they won't be exactly the same. Tech interviews are like college admission. You have to play the game by its rules. Algorithm and data structure questions are a part of that, and you need to be good at them. So think of algorithm interviews just like SAT exam for university admission. Since there is no standardized examination for algorithms, each company do their own interview, but that's a necessity to be admitted to a job in a higher level company, and you need to play this game, unfortunately. Code for all these questions and answers along with their tests are on GitHub, and the link is in the video description below. So let's move on to the second question. This is a medium difficulty one, and we're going to use dynamically sized sliding window. So our question, given an array of positive integers, find the subarrays that add up to a given number. Here's our example input, bunch of positive integers, and desired sum is 7. This is different from the previous problem. In the previous problem, we were bound to have a subarray of size 2. In this one, we can have a subarray of any size as long as its sum is 7. So as always, let's start with the requirements analysis. Subarrays are contiguous by definition, and I will have a separate video on the subtle details between subarrays, subsets, substrings, and subsequences, and more. So watch out for that. The input size could be anything. It could be the first 10 to the 10 decimals of pi. So again, the input size is unbound. So the memory use have to be constrained. No negative numbers or zero to deal with. It is hard to deal with negative numbers and zeros with a dynamically sized sliding window. You're going to see why that is the case in the next question. But for now, let's continue with our analysis. The input size is unlimited again, so we have to be careful. And yet again, we store all possible variations of all possible subarrays in the memory, and we cannot use recursion. And as always, I would like to repeat that you should think about all the data structures before jumping into coding. So let's implement the brute force approach. We will find all possible subarrays and calculate their sum and put them in a map. Then we will return the subarrays that add up to the desired sum from that map. So let's calculate. We're going to find the first subarray sum, which is 1. And we're going to find the second subarray sum, which is 8. And we're going to find the third subarray sum, which is 12. And we're going to find the fourth subarray sum, which is 15. And it goes like this. And then we're going to move on to the second member. We're going to calculate the 1, 2, 3, all of it all the way to the bottom. And we're going to move on to the third one, calculate this again. So this is ridiculously CPU intensive. And the time complexity n times n plus 1 divided by 2. And why is the case? Now, with the first element, we are doing n steps. With the second element, we are doing n minus 1 steps. And with the third element, we are doing n minus 2 steps. And the formula for this series happens to be n times n plus 1 divided by 2. Obviously, this is unnecessarily precise. There are a lot more going in the time complexity than just this algorithm. The programming language you use, libraries you use, they all affect the time complexity. So you are not expected to find the time complexity as precisely as this. All you have to find is a rough estimate, just to show that this is an exponential time complexity. And the space complexity happens to be the same. Again, you don't need to show this. All you are expected to show is the exponential space complexity. Now, how to improve this solution via reusing subarray sums? While we are calculating the subarray sums, you can see that the ones in between get recalculated over and over again. So we can somehow reuse these sums. We won't end up having n squared time complexity. How can we do that? Obviously with sliding window. So let's do it. We'll start by calculating window sum, starting with the first element. Then we're going to expand or shrink the window by 1, depending on whether our subarray sum is greater than or less than 7. So let's do it. We'll start with 1. The subarray sum is 1. We're going to move on to 2. The subarray is 8. So we're going to have to shrink the subarray. So let's do it. We shrink it by 1. And there we go. The first subarray that satisfies our constraint and adds up to 7 is just 7. So we're going to expand it again, and it's going to be 11, which is above 7. So we will have to shrink it, and it's going to be only 4. Then we're going to expand it, it's going to be 7, and there we go. We found the second subarray that adds up to 7. And we're going to continue expanding it, it's going to be 8, which is more than 7, so we're going to have to shrink it, which is 4, and we're going to continue doing this, and find all the subarrays that add up to 7 and just return them. And the time complexity is O(n) because we are processing each element only once while we are sliding the window. And that ends up being linear time complexity. And the space complexity is O(n) because O(n) means the worst possible case. So let's imagine the worst possible case. The worst possible case is an array made up of members 7, 7, 7, 7, 7. So in this case, we're going to have to store the indices of this window, this window, this window, and this window, which will end up being n windows. And it's going to end up costing us O(n) space. Always remember that big O notation means the worst possible scenario. So you should be calculating that. This is the worst case. So let's move on to the variant of the second question. This is again a medium difficulty one, and we're going to use a modified dynamically sized sliding window. So here's the question. Given an array of integers, which includes negative, 0, and positive, find the subarrays that add up to a given number. And here's our example input. It has some negatives and 0 in it, and the desired sum is 5. So we're going to find a subarray that adds up to 5, just like this, or just like this. So the brute force approach, we know how it is done. We find all possible subarrays and all their variations and store them in a map, and just look it up from that. Obviously, that's not a good solution. Optimum solution is Cadane's algorithm. Time complexity of Cadane's algorithm is O(n), and since this video is not about Cadane's algorithm, I won't go into that, but I'll have a separate video on that. But for this video, we can still use sliding window approach with a modification. So let's investigate why we can't apply sliding window with the negatives in it. So let's try doing it. Let's calculate the first subarray sum, which is -1. Let's expand it, -5. Let's expand it, it is still -5. Let's expand it even more, that adds up being to 0. Let's expand it one more, that adds up to being 3. Let's expand it by 1, that ends up being 5. And this is the very first subarray sum that is valid, that adds up to 5. So we're going to start shrinking it. So this adds up to 6. We're going to shrink it more. This adds up to 10. We're going to shrink it more. This is still 10. And this is 5. So we found the second one. This and this entire thing, they both satisfy the conditions. But what happened to 5? Just 5 itself is also a valid solution. But why couldn't the sliding window find it? Let me tell you why. By the rules of the sliding window, you need to be expanding the sliding window, and the sliding window should be growing. But when you have negatives, the sliding window is actually shrinking in total value, which breaks the algorithm itself. So what you can do about this is quite simple. So you find the lowest possible member of the array, and you increment the array by such a number that even the lowest possible member is going to end up being positive. So if we increment everything by 5, this is going to be 1, this is going to be 4, this is going to be 5, and we'll have a new array, and on that new array, we can apply the sliding window technique. Then find a valid solution. But I don't recommend doing it because this adds complexity. The Cadane's algorithm is much simpler, and you will have to wait for that. So let's get to the question 3. Again, this is a medium difficulty 1, and this time you're going to apply the sliding window with flipping and swapping. Let's see how it goes. Given an array of 0s and 1s, find the maximum sequence of continuous 1s that can be formed by flipping at most k 0s to 1s. So let's check our example input. We have a bunch of 0s and 1s, and we have maximum of 2 flips. So we can flip this to 1 and this to 1, and we're going to end up finding the maximum possible 1s that can be formed. But before jumping into coding, we always do requirements analysis. So again, the input could be anything. It might even be all the 0s and 1s on your hard drive. So again, we'll have to watch for the memory. The interviewer might ask you to return the subarrays that satisfy the given constraints to make the question harder. In most cases, you're just going to be asked to find the length of this maximum subarray that satisfies the condition. But if the interviewer wants to make the question harder, they will ask you to return the starting and ending indices, all the subarrays that satisfy the given constraints. So let's do the analysis. You should be preferring simple iteration over recursion. And if possible, you should write tests. There might be corner cases that you might not think about while writing your algorithm, and writing some basic tests will help you with that. Optionally, you should start by writing some tests to demonstrate your test-driven development skills. So if you write some tests, including for corner cases, then write your algorithm, you're going to get the highest possible marks for the interview. But obviously, to be able to do that, you should be in command of your algorithms. And again, the solution and the test code for these questions are in the QuanticDev GitHub repo. And again, the link is in the description. You can also check out my video on test-driven development and other software patterns. The link is also in the description. So let's start by implementing the brute force approach. In this approach, we're going to find all possible subarrays of the given input and calculate how many zeros they have in them. And amongst the subarrays with 2 or less zeros in them, we're going to return the longest one. So let's do it. We're going to calculate all possible subarrays, just as we did in our previous brute force solutions. Then we're going to calculate how many zeros they have in them. Like this one has 2, this one has also 2, then this one has 1, this one has 1. And we're going to find the subarray that has 2 or less zeros in them and has the maximum possible length. And again, the time complexity is going to be roughly O(n) squared, because we're going to have to calculate every subarray over and over again. And the space complexity is again going to be O(n) squared, which is kind of unacceptable. So let's implement a more optimum solution using sliding window. We're going to start by checking for elements to flip, starting the first element. Then we're going to flip zeros until we reach the limit. So let's do it. We'll start with our first sliding window of size 1, and we have to already flip 1. So let's expand it by 1. We're going to still have to flip 1 because we have only 1 0. And let's expand it by 1. And now we used both of our flips. Let's see if we can continue expanding this. Yes, we can, because we found another 1. And let's see if we can expand this further. No, we cannot. To be able to expand it further, we would need 3 flips, but we only have 2. So we're going to have to shrink the window. And we are back to 2 flips. Let's expand the window. And we are back to 3 flips. So let's shrink the window. And we are still 1 flip too many. So let's continue shrinking it. And we are back to 2. So let's expand it. We are still 2. So we are still 2. This happens to be the longest possible subarray that has continuous ones with at most 2 flips. And then we're going to unflip zeros from the left and continue flipping from the right to slide the window. The time complexity is going to be O(n), and the space complexity is going to be O(1). As always, we'll only have to store the current indices of our sliding window and the maximum one that we found up to that point. Let's jump on to the final question. Now, this is a hard one, and it uses sliding window on strings. Let's see why it is hard. Given a string and n characters, find the shortest substring that contains all the desired characters. Here's our example input string. Here's the desired characters. Now, before coding, let's do the requirements. The substrings are continuous by definition, so the characters should be adjacent. Just as we did with the subarrays, we can only have adjacent characters in a substring. Given string could be of any size. It can even be the entire Harry Potter series. So again, we'll have to watch out for memory. This is similar to numeric sliding window questions, hence similar principles apply. Again, we'll have to avoid recursion, and we'll have to keep in mind that both given string and the desired characters can have repeating characters. So this question is a lot harder than it looks. So instead of being asked for ABC, we could be asked for ABC, 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 which will make this question a lot harder. So you need to account for that too. Well, I would personally not ask this question unless I'm interviewing for a senior position, as most juniors will not be able to come up with an answer in 30 minutes. Let's try and implement the solution, so you're going to see why that is hard. The brute force approach is always we're going to find all possible subarrays of all combinations. Then we're going to check each substring to see if they contain all the desired characters. And finally, we're going to return the shortest one of the matching substrings. The time complexity is again going to be exponential, and the space complexity is going to be again exponential. This could theoretically be useful in a CPU-sensitive application, like in a web service. We could generate and cache all substrings and use them. The consecutive lookups would have a time complexity of O(1), but obviously this would require a lot of memory. So let's implement the optimum solution here. With the sliding window, we're going to start checking for the needed characters from the left. We can expand the window from right until all the needed characters are found. And finally, we're going to shrink the window from left while keeping track of the removed needed characters. So let's go ahead and do it. We'll start with this. Does that contain any of the desired characters? No. So we should expand it. Then we have FA. It contains one of the desired characters. So let's continue expanding it. 4, it's not something that we need. Let's expand it. We found C, yes, that we need it. Expand it. H, we don't need it. Expand it. B, yes, we need it. So this substring contains all possible desired characters. So what we do here is to shrink it by 1. So we eliminated f, but it's not a desired character. So this is still the shortest substring that has all the desired characters. So let's continue shrinking it. Oh, a is gone. So we have b and c, but not a in the substring. So what we should do is to expand it. We found a again. So this substring again contains all the desired characters. So we're going to continue doing this and find the shortest substring that satisfies the constraints. Now let's get back to why this is a difficult question. If you are given desired characters like a, b, c, c, you will not only have to keep track of the first c, but also the second one. Let's say that you found this, it contains a c, but we still need another one. We'll not only have to keep track of the desired characters, but how many of them we need. If you check out the solution in GitHub, you're going to see that it has a lot of lines in comparison to other solutions, which is needed to account for this fact. So the time complexity is O(n), and the space complexity is O(1), which is exactly the same as other sliding window solutions. I won't write down the code for the solution here, so it's up to you to check out the GitHub and read the solution and its tests. So here are some final tips. The coding interview measures if you are going to be able to write code in the first place, think independently on technical problems, think analytically, and explain and discuss your ideas, and reason about arbitrary problems and constraints, and finally, operate under pressure and still deliver results. Obviously, being given 3 questions and 45 minutes to solve, 1 easy, 1 medium, 1 hard question, it's somewhat challenging, and that requires preparation. If you are prepared for it, and if you can think independently, write good code, and reason about arbitrary problems, you're going to be successful. And that is exactly what the coding interview is measuring. And that is it. If you'd like to see more algorithm videos, give the video a thumbs up. And if you want to see the upcoming interview question videos, don't forget to sub. And I'll see you in the next algorithm video.